Okay guys, in today's video I'm going to go over antennas and their placements on vehicles and the effects of the return loss that it has depending on where you install them on the vehicle and what kind of metal situation you have around it. First, I want to make sure we have a definite understanding of the difference between return loss and radiation pattern. When an antenna is placed on a particular part of a car, the radiation that comes off that antenna will, if you're looking down from it from space, will have a particular shape depending on where exactly on the vehicle the antenna was placed. And it can vary a lot depending on other factors, as in, is there something metal blocking it that's at a higher relative height than the antenna is wherever it is mounted. So you basically have a shadow wherever that higher metal is. But anyway, then there is return loss, which deals with the idea of how effectively you're able to transform the electricity coming down the coax into electromagnetic radiation. And that's it doesn't really care how it's radiated as long as it gets radiated and not returned to be dissipated as heat at the radio. So just wanted to clarify those two things as we take a look. The first thing I wanted to show was some reference sweeps and to clarify what it means by bandwidth and how we're going to be doing these measurements. So the first antenna we're looking at is a quarter wave antenna on a 3x3 aluminum sheet. And this is kind of like an ideal antenna, ground plane. You have the minimum amount that you needed. Of course, the more metal, the better. But this is enough to get you a good return pattern. And what we're seeing over here is that if you draw down the lines from the references at -10, the VSWR 2 to 1 is right here at 9.5 return loss. So if you pull down the lines from the 9.5 crossings of the return, the distance in between here, the amount of signal is going to be your bandwidth. So that's how we're measuring bandwidth. It's whatever drops below the 9.5, and for the amount of frequency spread that it is underneath the 9.5 mark. So, but anyway, we're going to start off with quarter wave on 3x3 aluminum as our reference, and then we can go to the half wave on 3x3 aluminum. And when you look on with the half wave, you'll see a very similar bandwidth, but you're able to get a much sharper notch on your return loss. So this gives you the ability to really tune it in to where you get essentially no reflected power on your transmitter. And that's the ideal, is because you really want to try and shoot for 20 dB if you can. So you have a good window of 20 dB right here. So anyway, let's move on to the next one, which is quarter wave on steel. And you can see that steel is not quite as good as aluminum when it comes to ground plane, but it's still very good. And there's no problems with it. And so let's take a look at the next one, which is going to be the half wave on steel. And once again, just not quite as good as on aluminum, but very similar in its sweep. So those are going to be our kind of reference points of like those would be the ones that were really good. So just kind of keep that in mind. Now we're going to go to the next one, which is I just wanted to show you this one, which is since we're on the steel, is to show you the quarter wave mag mount. And it's not quite as good as the hardwired one, but it's still really good. But don't be fooled by mag mount as far as using it as a transmitter. It's good as a receiver, but you don't want to use it as a transmitter because it ends up it's going to radiate off the coaxial cable. The current's got to go somewhere, so it doesn't have a ability to dissipate through the rest of the metal. So it creates what's called a common current, and you don't want that. So avoid the mag mount for any transmitters. Next, I wanted to show you what happens when you use an angle bracket. And I have a big chunk of aluminum here, which kind of would simulate a vehicle, and this is the effect that you get on a vehicle. And what it does is it ends up making the resonant frequency shift. In this case, it moved it over by almost 10 megs. So now it's resonating at 145. So in order to pull this back over, you would need to shorten the antenna. You'd have to cut it some to get it back over here, like a ½ inch, an inch. So this is an example of anytime you put one of these antennas in a weird spot, it could change not only the return loss, but it can change the resonant frequency. So this is, like I said, now you're going to have to cut this at an oddball length that's not going to match the cutting chart to get it back over into the right position. So if you take a look at this same setup here, except now we're using the half wave. Well, the half wave antenna isn't affected with its resonant frequency being shifted, but it is got a little bit of a tighter bandwidth, and not as much as it usually has. You can see the V is really sharp here. And it might have shifted over just a little bit on the resonant, but not much. But overall, a much better performer as far as the half wave is concerned, if you can get the tuning right. So, all right, let's look at the next example, which is what happens if you get an antenna mounted somewhere, but it's right next to a large piece of metal, whether it be a pipe or other piece of thing on a vehicle or whatever it is. And here I have a large aluminum plate, about 6 or 7 inches away from the whip. And what you see, what it does is that it does not affect its resonant center frequency. However, it greatly reduces its overall return loss. As a matter of fact, it doesn't have a single dip below 9, so it technically wouldn't qualify to pass at any frequency. And there's nothing you can do about a situation like this except this, which is break out your half wave. And now you can see that your half wave is definitely going to be able to get all of the performance that you need and bandwidth, but it does definitely affect its resonant frequency. In this case, it moved it up. So what you're going to have to do for this one is the whip would need to be longer. You would need to do an oddball cut to pull the dip back over this way to get it centered back where you wanted it. So this is another example of how if you can't do a sweep like this, you really can't get an idea of what's going on and which way to go. I've done it manually through the watt meters by just sneaking up and eventually creeping up on a dip and then finding out, well, that's it. But it's just this is so much easier. All right, now let's take a look at the next one, which is what happens when you have not enough ground plane. And I'm using a little chunk of steel here, and it's nowhere near long enough as far as um, um, being able to lay this quarter wave down and rotate it around. So it's ground plane deficient. And what this ends up doing is it changes its center frequency by a lot. And in order to pull this back, you would need to increase the whip length. And I just wanted to show you guys a really quick trick to just confirm your sanity and make sure that that's what it is and that you're going to be able to do the right amount of length. And that's just taking a piece of solder, a couple loops of solder, and wrapping it around the top of the antenna and having a little bit poke up the top to give you virtually a taller antenna. And that's what it looks like. You wrap the solder around so it's poking up. And you can actually, when you get the tension on it, you can slide it up and down and custom get the right length. But over here, I'm showing you that same antenna now. That's now properly centered to where it's supposed to be. And this is what you would need to, like I said, cut the whip now for the standard cutting chart, plus this inch or two that you knew you had to add. Next thing I wanted to show was the why you don't ever put any of these antennas on the ground, because you'll get an incredible return like this. It's even more dramatic when you put like the big aluminum plates on the ground. You'll see this return go all the way almost in, it looks like into infinity. And what it is it is in fact true. It's not an illusion, but it doesn't work like you think it would be. Like I thought it would be. After I researched it, I found that when antennas are close to the ground like this, and your ground plane essentially binds itself to the earth itself, that it essentially acts like a giant sponge. So a lot of this radiation, instead of going out and radiating everywhere, a lot of it will be absorbed in the ground and nowhere near as much coming out as you would think. So be careful about anytime you're doing antenna measurements that you got them elevated far off the ground, because you will get this bogus effect on your return loss. Okay, guys, that's it for the antenna placement. And just like I said, keep that in mind whenever you're putting an antenna in an odd spot. You've probably changed something about it. More than likely, it's going to be its resonant center frequency. So you'll have to cut and tune as needed. Okay, we'll talk to you soon.